Welcome back to another explainer. Okay, let's dive right into this because today we're shrinking way down into the microscopic world of organic chemistry. Now, if you think chemistry is just a bunch of random letters and lines drawn on a whiteboard, well, think again. What we're really looking at today is a high-stakes molecular drama. We are going to break down the highly complex, exact steps of how atoms interact, fight for position, and completely transform. Our main event for this explainer, the unimolecular nucleophilic substitution reaction, or, as you probably know it, the SN1 reaction. To really grasp this drama, we first need to set the stage with nucleophilic substitution. So let's break that down. A nucleophile is essentially an atom or molecule that always carries a negative charge, and it's constantly on the hunt for a positive partner. Now picture an alkyl halide molecule. Inside this molecule, the halogen, let's say it's a chlorine atom, is way more electronegative than the carbon it's attached to, so it greedily pulls the shared electrons towards itself. This leaves the chlorine with a partial negative charge, acting as our weak nucleophile, and it leaves the carbon with a partial positive charge. And that's exactly when a new, strong nucleophile enters the scene. What happens next is perfectly captured by a pretty blunt rule. Strong people always rule over weak people. In this molecular world, it's absolutely ruthless. The strong nucleophile will always replace the weak one. It's essentially an eviction. The strong nucleophile just forces the weak one out and takes its place on the carbon atom. And that whole replacement process, that's the beating heart of nucleophilic substitution.
Enter SN1, the two-part heist.
Now, tertiary alkyl halides heavily favor this specific SN1 reaction. But why call it a two-part heist? Well, unlike some reactions that just happen in one chaotic crash, SN1 is highly calculated. It happens in two very distinct sequential steps. The whole thing plays out like a deliberate two-act play. Step 1 is the formation of a carbocation, and Step 2 is the attack of a nucleophile. You literally cannot have the second without the first. Let's zoom in on exactly how this complex mechanism actually works.
Act 1 is what chemists actually call the slow step. You start with your tertiary alkyl halide, and to kick things off, you introduce a polar solvent. This solvent acts kind of like an instigator. It polarizes the molecule. Because of this, the weak halogen nucleophile breaks away entirely. It just packs up and leaves. And because it takes those shared electrons with it, the carbon atom left behind suddenly becomes positively charged. This brand new positively charged molecule is what we call a carbocation.
To really visualize the physical change happening here, look at this specific number. Before that weak halogen broke away, the original tertiary alkyl halide molecule had a very strict 3D shape. The angle between the carbon atoms was exactly 109.5 degrees. It's cramped, it's highly specific, and honestly it's stable. But the split second that halogen leaves, boom, 120 degrees. The carbocation is formed and the entire geometry of the molecule physically shifts. The atoms literally spread out, taking up space. The angles between the carbon atoms widen from 109.5 all the way to 120 degrees. This spatial change is the absolutely crucial physical result of that slow first step. The stage is now perfectly set for Act 2. And now the pace drastically speeds up. Act 2, the attack. We've got our carbocation completely exposed with its wide 120-degree angles and a positively charged alpha carbon. The strong nucleophile, that powerful incoming molecule we talked about, sees this wide-open target and violently attacks the alpha carbon. Because the weak nucleophile is already long gone, the strong one can just swoop right in and bond without any interference. But here's the catch. How does it attack? Well, because the carbocation is now somewhat flat and open, the strong nucleophile actually has two completely different pathways to strike. If it attacks from the right side, the molecule retains its original structural shape. We call this a retention of configuration. But if the nucleophile swoops in from the left side, the final molecule's shape actually flips. That's an inversion of configuration. And since both sides are equally exposed, it's basically a coin toss, resulting in a perfect split, 50% retention, 50% inversion. Before we move on, let's quickly review the speed limit for this SN1 heist. The structure of the starting carbon totally dictates how fast this two-step process can happen. A third degree, or tertiary carbon, is the absolute fastest at pulling this off. A second degree is a bit slower, and a first degree, or primary carbon, is the absolute slowest at completing an SN1 reaction. Which leads us to a massive plot twist in our microscopic drama. If primary alkyl halides are incredibly slow, like practically terrible at the SN1 reaction, what do? I mean, they don't just sit there and do nothing, right? Of course not. They just use a completely different playbook.
Which brings us to the SN2 alternative, a one-step clash.
While tertiary alkyl halides love that two-step SN1 process, primary alkyl halides heavily favor this SN2 reaction. And guys, this isn't a calculated two-part heist. This is a simultaneous, chaotic one-step clash. In this scenario, the strong nucleophile doesn't politely wait for the weak halogen to leave. No way! It just charges right in. It attacks the carbon from the back while the weak halogen is still desperately clinging to the front. This creates a temporary, highly unstable transition state where the new nucleophile isn't fully bonded yet and the old one isn't entirely gone. It's a literal microscopic tug of war. Eventually, the strong nucleophile wins, forcing the halogen off. And because it attacked from the back, an SN2 reaction always results in an inversion of configuration. The entire shape flips. And this brilliantly illustrates how changing the initial conditions changes absolutely everything. Take a look at the speed rules for SN2. They are the exact reverse of SN1. Here, the first degree carbon is the fastest, the second degree is still in the middle, and the third degree carbon is the absolute slowest. So let's put them in the ring, the showdown. SN1 versus SN2.
So the crucial point here is that a molecular substitution is never just random. It's governed by a very strict set of structural rules. Let's look at them head-to-head. SN1 relies only on the concentration of the alkyl halide, meaning it's a first-order reaction. But SN2 relies on both the alkyl halide and the incoming nucleophile, making it second-order. As we saw, SN1 is a deliberate two-step process that favors third-degree halides, uses polar solvents, and crucially, forms that temporary carbocation intermediate. SN2, on the flip side, is a one-step rush favoring first-degree halides and nonpolar solvents, and it forms zero intermediate carbocations.
The contrast keeps going when you look at how they handle structure. Because SN1 forms that wide-open carbocation, the products can actually rearrange themselves, and the attack can come from both sides, giving us that 50-50 split. It can even get away with using a weak nucleophile. SN2? Absolutely no rearrangement possible. The attack happens strictly from the backside, and it absolutely requires a strong nucleophile to force the issue. It's wild how these shifting conditions completely dictate the chemical outcome.
So, we've unpacked the slow, shifting angles of the SN1 two-part heist, and the aggressive, one-step clash of the SN2 alternative. It's honestly mind-blowing to think that this level of precise, mechanical conflict is happening constantly, forming the literal building blocks of our reality. So, I'm going to leave you with this. The next time you look at the physical world, will you recognize the invisible, microscopic power struggles happening in the matter all around us? Chemistry isn't just boring rules in a textbook. It's an ever-ending series of tiny, dramatic, and fascinating heists. Thanks for exploring this with me today, and keep your curiosity focused.